Welcome to Math 154 videos. This video is going to cover the derivative of logarithmic functions, and we're going to recall that the derivative of the natural log of x is 1 over x, and we're going to use that to differentiate this function. So we're going to go ahead and start off by taking the derivative of our outermost function, which in this case is the natural log of a bunch of stuff. So we're going to start by doing that, and then we're going to apply the chain rule in order to differentiate the entire function. So our natural log, when we take the derivative, becomes 1 over all the stuff that was inside, which in this case is the sine of x to the fourth plus 2x. So all of that stays under that 1. So there's our first step. Now, by the chain rule, we have to multiply that by the derivative of what's inside this natural log function. So what's inside the natural log function next is a sine. So the derivative of sine is cosine, but instead of x in the middle, we have this x to the fourth plus 2x. So we're just going to add that right in there. And that means we need to use the chain rule again. So we're going to go ahead and take the derivative of what's inside the cosine function. So what's inside the cosine function is our x to the fourth plus 2x. So now we're going to multiply that by the derivative of x to the fourth plus 2x, which is 4x cubed plus a 2. And that's going to be it for our derivative, but it might look a little bit nicer if we write this as the cosine of x to the fourth plus 2x over sine of x to the fourth plus 2x times 4x cubed plus 2. That whole thing's going to be in parentheses. And we'll notice that tangent is sine over cosine, so cosine over sine is cotangent. So this is actually cotangent of x to the fourth plus 2x times 4x cubed plus 2. And that's going to be our derivative in the simplest form. So here's our second example, and you'll notice we have a function y is equal to x times the natural log of something. So we're going to have to use the product rule, with x being our first function and the natural log of the tangent of the natural log of x being our second function. So we're going to go ahead and do that. So y prime is equal to the derivative of the first function, which is 1, times the natural log of tangent of the natural log of x. And that's just because our derivative of x is just 1. So we're going to add to it now x times the derivative of the second function. Well, this is going to involve a couple of chain rules, but the important thing to notice is the outermost function is a natural log. So the natural log of x has a derivative of 1 over x. But instead of 1 over x, we're going to have 1 over everything that's inside this outermost natural log. So what's inside of it is the tangent of the natural log of x. Alright, so that's going to be our first step. Now we have to take the derivative of what's inside of that outermost natural log. So we move to our tangent. The derivative of tangent is secant squared, but instead of x, we have the natural log of x, because that's what was inside of our tangent function. And then we need to multiply that, again by the chain rule, by the derivative of the natural log of x, which is 1 over x. So now we have that x and this x canceling out because everything is multiplied together. And we can go ahead and rewrite this as the natural log of tangent of the natural log of x. And now we'll notice that tangent of the natural log of x, well, tangent is sine over cosine, So 1 over tangent is going to be cosine of the natural log of x over sine of the natural log of x. And then our secant squared is really 1 over cosine squared of the natural log of x. So these two cosines cancel out. So what are we left with? This stuff in the beginning still stays there. Natural log of x. It doesn't change. So we have a 1 over sine of the natural log of x times a 1 over cosine of the natural log of x. Alright, and that's it. We can't really simplify that anymore unless if we want to rewrite our 1 over sine and 1 over cosine as secant and cosecant, but this is pretty much as simple as it's going to get. So that is our final derivative.